Hello everyone, and these screencasts are so weird. I always want to say like, welcome back to my channel. I'm your host, Mrs. Stewart. Today we're learning about power. So you guys have already heard this term before, right? Power. So right here on the screen, it says a powerful lineman is both strong, which means that he applies a big force, and fast, which means that he displaces objects in small times. So that's kind of what the equation of power says. And so today what we're going to do is we're going to put physics terms and an equation in for what you already know about power. So the definition of power is the rate at which work is done on an object. So when we look at the equation for this, we see that power is work over time. So if we insert our equation for work, which you guys learned last week, power is equal to F, force, times displacement, times the cosine of theta over time. So all these variables, W is equal to work, T is time, F is force, D is our distance or displacement, and then that theta is the angle between force and displacement. Remember, that was really important. We talked about that last week. So if we kind of examine this equation a little bit further, we can see that to be powerful, something either has to do a lot of work in a given amount of time. So that first slide said that the lineman is strong. There's a lot of force, which means that there's a lot of work done. So work is large. You can see that power and work are directly proportional to one another because power is equal to work, which is on the numerator. So that means they're directly proportional. Or that thing does work in a short amount of time, right? Which means that T is small, so it's very fast. And again, we saw on that first slide that we had the lineman, he's very fast, he's quick, and he's strong, very powerful, okay? And you can see that T, our time, is on the denominator, which means that if it is small, then P, power, is going to be large because those things are inversely proportional to one another. Now we know a high-powered engine does work rapidly, and a powerful engine can get an automobile up to a given speed in less time, so it's quicker than a less powerful engine can. And we'll do an example with a car going fast in a bit. All right, so another equation that we get for power has to do with velocity, and I'll show you how we get that. So we know power is work over time. If we plug in our work equation here, we're just not going to use cosine because we're just going to assume that the force is in the same direction as the displacement, which means that that angle is 0, right? When they're in the same direction, the angle between the two is 0, and therefore the cosine of 0 is just 1. So we're going to drop that for now. Now we know that work is equal to force times displacement over time. So we get that power is equal to force times displacement over time. Now, if we kind of rearrange that a little bit and you see this displacement over time, that should look familiar. And if you remember that's constant velocity. So that's the constant velocity equation, displacement over time. So we end up getting also that power is force times velocity. Now, if we also insert our cosine equation, so we'll cosine into the equation. So this is if like our force is at an angle to the object or an angle to the displacement, then you would use this version of the equation. So power is equal to force times velocity times the cosine of the angle. So this equation is used when we are going at a constant velocity. If we have an acceleration, then you can't use this equation because velocity is not constant. Now the units of power is a joule per second because it's work over time. So that's also known as a watt. This was named after James Watt. 1 watt of power expended when 1 joule of work is done in 1 second. A lot of the time we'll use kilowatts. You've probably heard that before. And that, of course, is equal to 1,000 watts, just like kilograms is equal to 1,000 grams or kilometers is equal to 1,000 meters. So that's the same conversion you've heard before. 1 megawatt, which is a big M, that's 1 million watts. And then in the United States, we usually use units of horsepower, or we use electricity in kilowatts. So that's probably why you've heard that term before, but either may be used. The conversion for horsepower is 1 horsepower is equal to 0.75 kilowatts or 750 watts. It's actually, I think, about 746, but 750 is fine to use. All right, so today we're going to do 5 different examples. I know that's kind of a lot, but a lot of them are very similar to ones on your homework. And also, I kind of noticed that some of the homework problems from last week were a little bit more difficult for people. So I was thinking if we do more examples, then hopefully it'll be a little bit easier for you guys. All right, so example number 1, we have while working out, Dave pushes this 120 kilogram sled with a force of 175 newtons. If he is able to push the sled a distance of 20 meters in 5 seconds, what is his power output? So first and foremost, we're going to write down our givens. So our givens, we know that Dave is pushing a 120 kilogram sled, so that's our mass, 120 kilograms, and his force, F, is 175 newtons. It also says he pushes the sled a distance, D, of 20 meters in a time, T, of 5 seconds, and we want to know what power is. Now, I've already written down theta is equal to 0. Here we're kind of assuming that his force is in the same direction as the displacement. He's pushing horizontally. So since they're in the same direction, the angle between the two is 0. So I can just kind of assume that, especially since they don't give me an angle here. And then we want to know what the power output is. So let's write down our equation. We have power is equal to work over time. Now work we know is force times displacement times the cosine of theta. And then so we can plug that in for our work equation. And now all we have to do is plug in our numbers and solve. So we get power is equal to the force 175 newtons times the displacement 20 meters times the cosine of theta, which was 0, divided by time, which was 5 seconds. So now we can just plug into our calculator and solve. We end up getting 700 watts. Now you may notice that we didn't even need to use our mass in this equation. There are going to be examples where we do have to use mass. So I'll do a couple of those for you guys today too. So that was example number 1. Okay, example number 2, we have a Porsche 918 Spyder, however you say that, can accelerate from 0 to 60 miles per hour, which is 26.8 meters per second in 2.2 seconds. If the mass of the Spyder is 1,700 kilograms, what is the power rating of this engine? So again, let's write down our givens first. So we get givens. We know that it accelerates from an initial velocity of 0. So I have initial velocity 0 meters per second to a final velocity of 26.8 meters per second. And the time for that is 2.2 seconds. Now we know the mass of the Spyder is 1,700 kilograms. Or 1,700 kilograms, same thing. And we want to know what the power rating of the engine is. Okay, so if we look at our power equation, we know it's work over time, okay? Now, the work equation that we just used was force times displacement times the cosine of theta. We're not given a force here, right? We're not given a displacement here. We're not given theta here, but we could kind of assume, again, that theta is 0. But we're not given those things in order to find work that traditional way. Now, there is another equation that you guys learned for work or net work last week, if you remember. So the work kinetic energy theorem, remember, we know that work or net work really is going to change the kinetic energy of an object. So when we put a force on an object over a certain period of time, over a certain displacement here, we are going to make it go faster. So we're changing the kinetic energy. So that's what we're going to use here. Work is equal to the change in kinetic energy. Okay, now remember, change in kinetic energy, it's always final kinetic energy minus initial kinetic energy. Whenever you have that delta, it's final minus initial. We know kinetic energy is 1/2 times mass times velocity squared. So I'm going to plug those things into this equation. So we get work is equal to 1/2 times mass times final velocity squared minus 1/2 times mass times initial velocity squared. So let's plug in our numbers and find the work done here. So we get work is equal to 1/2 times the mass of the Porsche, which was 1,700, times final velocity, which was 26.8 meters per second squared. And then I just have minus 0 because the initial velocity was 0. So 0 times anything is 0. So that whole term ends up being 0 there. So plugging this into my calculator, I end up getting that the work done is 610,504 joules. So now we're going to take that number, plug it into our previous equation for work, and get that power is equal to work, which is that number divided by the time. So we get 610,504 joules divided by 2.2 seconds, and we end up getting a power of 277,501.8 watts. Now, of course, with cars, this doesn't really make sense to us, right? We're used to talking about cars in terms of horsepower. So you guys remember that 1 horsepower is equal to 750 watts. We can then divide this number by 750, and we end up getting about 370 horsepower for that Porsche. Now, I did end up looking this up because I was very curious, and it's actually the power rating of this Porsche's engine is actually much, much higher. I forget what exactly it was, but it was like twice this, I'm pretty sure. Now, the reason for that, then why this math didn't really work out, is because this equation right here, this work is equal to change in kinetic energy, that's the net work of the object. So we didn't take into account that there are frictional forces both in the engine and in the outside world that are taking away from the work done by the engine. So the work done by the engine is actually much, much higher than the work that we got here. And because the work is much, much higher, we would get a much, much higher power rating. So that's why, if you're curious, but I was very curious. But if we knew the work done by friction, we could really figure out mathematically the work done by that engine. All right, example number 3. So we have an elevator motor lifts 800 kilograms of mass to a height of the 5th floor of an office building, which is 20 meters above ground level, at a constant speed of 3.5 meters per second. What is the power rating of the elevator motor? So for this first example, example number 3, we're finally moving upward. Okay, so examples 3, 4, and 5, we're going to do examples where we're actually moving upward. The other 2 were just horizontal motion, so they're a little bit different when you do stuff like this. But first and foremost, I want to write down my givens, just like we've been doing. So I know that the elevator motor is lifting an 800 kilogram mass, so M is equal to 800 kilograms. The height of the 5th floor is 20 meters, so that displacement upwards is 20 meters, and then the constant speed is 3.5 meters per second, so V is equal to 3.5 meters per second, and we want to know the power rating of the elevator motor. Now, the other thing about this is, well, first and foremost, you should notice that it says that we're going at a constant speed. So when it gives you that constant speed, usually you're going to use the equation with power with velocity in it. So that was power is equal to force times velocity times the cosine of theta. Now, the other thing about this is we don't know what the force is, right? What is the force of that elevator motor pulling it upwards? Well, in order to know that, we're going to have to draw a free body diagram. So drawing our free body diagram, there's our force of the elevator motor. We know that it is a cable pulling it up, so I'm going to label that force tension. And then we also have the force of gravity going downward on that elevator. So there's our free body diagram. Now, is there an acceleration here? Your answer should be no, right? It says that it's moving at a constant speed, which means there's no acceleration. Okay, no acceleration, what does that tell us about our forces? It tells us our forces are balanced, right? We have balanced forces. We have no net force and therefore no acceleration. So that means force tension is going to be equal to the force of gravity, okay? So force tension, which is the force of the elevator motor pulling that elevator upwards, will be equal to the force of gravity, which is just mass times the acceleration of gravity. So what I'm going to do is plug in mass times acceleration of gravity in for our force in the power equation. Okay, now the other thing here is, what is our angle? Now again, we're moving upwards. The force of the elevator is also upwards, so the angle between those two, the force and the displacement, is 0. So we also are going to plug in 0 for our angle. So let's plug in our numbers. We get power is equal to the mass, 800 kilograms, times g, which is our acceleration of gravity, 9.8 meters per second squared, times the velocity, that constant velocity of 3.5 meters per second, times the cosine of the angle, plugging this into our calculator, we end up getting 27,440 watts for our power rating of the elevator motor. Okay, two more. Example number 4. So we want to calculate the power expended by a power lifter when she lifts a 100 kilogram barbell over her head, which is a distance of 2 meters in 1.5 seconds. So I'm going to actually start this one by drawing a free body diagram. So just like we did for the elevator, I know here's my barbell. Isn't it beautiful? Yes, I know. So the barbell has a force of gravity or a weight downward. And then the weightlifter is going to be applying a force upward to pull it up and over her head. So we have a force applied upward. Now we're going to write down our givens. Now we have the mass of the barbell is 100 kilograms. We know that she's lifting it over her head, a displacement of 2 meters, and that time is 1.5 seconds. Okay. Now, after this, we want to write down our equation. So we want to know what the power expended by that weightlifter is. So, again, sorry, I forgot to mention this. Again, we are moving upwards, right? So the displacement is up, the applied force is up. Again, our angle is 0 because the angle between the force and the displacement is 0. They're in the same direction. So our theta is equal to 0. So our equation here is that power is equal to work, which is force times displacement times the cosine of theta over time. Now again, the question here, first and foremost, is what is that applied force? So it doesn't specifically say that in these type of equations, but what we can do is we can basically just assume that she's applying at least the force, the weight of the barbell or the force of gravity of the barbell in order to lift that thing up and over her head. So we kind of assume that it's moving at a constant velocity. So we're going to assume the lifting force is equal to the force of gravity. So we're assuming a constant speed. So because of that, force applied is equal to the force of gravity, which is just mass times acceleration of gravity, just like it was in the last problem that we did with the elevator, okay? So we end up plugging in mass times acceleration of gravity for our force applied times displacement times the cosine of theta over time, and now we can just plug our numbers in and solve. So we end up getting power is the mass, which is 100 kilograms, times acceleration of gravity, 9.8 meters per second squared, times displacement, 2 meters, times the cosine of 0, divided by the time, which was 1.5 seconds, and we get a power of 1,306.7 watts. Okay, all right, last but not least, example number 5. Now this one is basically, well, almost exactly the same as one of the ones on your homework, so I wanted to make sure that we went over this. The numbers are a little bit different, so you're gonna have to do it over again yourself. So we have a escalator is used to move 25 passengers every minute from the first floor of a department store to the second. The second floor is located 8 meters above the first floor. The average passenger's mass is 65 kilograms, and we want to determine the power requirement of the escalator in order to move this number of passengers in this amount of time. So first and foremost, let's write down our givens. We have that the escalator is moving 25 passengers every minute, and also later it tells us that each passenger's mass is 65 kilograms. So if it's moving 25 passengers each with a mass of 65 kilograms, we can find the total mass that elevator is moving. So how do we do that? We just multiply them together, right? So we get each person is 65 kilograms times 25 people, and that equals 1,625 kilograms. Now next, it tells us that this is happening every minute. So in physics, do we use minutes? You should have said no, I hope. We use seconds, right? So in 1 minute, there are 60 seconds. So that's our time period for this problem. And then it says that it's moving the people from the first floor to the second floor, and the second floor is located 8 meters above the first floor. So our height here is 8 meters, okay? And then we want the power requirement of the escalator. So now let's draw a picture. So here's my escalator. Okay, it's a very good drawing, I know. I got it from the internet. So I'm also gonna draw a little person on this escalator. Now, I'm gonna draw a free body diagram. So you'll see that for a lot of these, I always write down my givens. I like to draw a picture a lot of the time and draw a free body diagram. So you guys should be doing this also when you're doing these problems. So a free body diagram of this person. Now, we have the force of gravity downwards, of course, the person's weight keeping them on the earth. And then we have the force of the escalator stairs on that person upwards. What do we call that force again? We call it normal force. I hope you said normal force. So F sub n, our normal force of the escalator stairs. Now, I want you to think about this. When you're going up an escalator, are you like speeding up as you go up there? No, you're not. You're basically going at a constant velocity. So because we're going at a constant velocity, again, we've been doing this for the last couple examples, that means we have balanced forces, right? We have no acceleration, the net force is 0, and therefore we have balanced forces. Now we're going to talk about that in a little while. Now, the other thing I want to draw this on this picture is the height of the elevator is 8 meters. So like I was just saying, because this escalator is taking this person up at a constant velocity, that means that the forces are balanced because there's no acceleration, there's no net force. So the normal force is going to be equal to the force of gravity. Okay, so normal force equals force of gravity, which is mass times the acceleration of gravity. And then the other tricky thing here is they don't give us a displacement like up the elevator, okay? They don't give us this distance. We also don't know this angle right here, so we can't find, you know, the angle between the force and the displacement or anything like that. So we can't use this as our displacement. Now, what we end up doing is we actually use our height as our displacement. Okay, and all we do here is when we use our height as our displacement, now we're going up 8 meters and the normal force is directed upward. So the angle between the two is 0. All right, so we also use that the angle is 0 between that force and that height that we get displaced. Okay, you guys kind of saw this on your It's All Uphill last week. Work here is really equal to the change in potential energy, if you guys saw that last week, if you remember that. Okay, so now we have all our information. Now we can solve. Okay, so we have power is equal to force times displacement times the cosine of theta divided by time. Plugging in for, remember, the normal force was equal to the force of gravity because we're going up at a constant velocity, so therefore forces are balanced. So we plug in mg for our force of the escalator stairs on that person, pushing them up. And then now we plug in our numbers. We get power is equal to mass, which is the total mass of that 25 people, 1,625 kilograms, times g, which was 9.8 meters per second squared, times the displacement, which was the height, 8 meters, times the cosine of theta, which was 0 because the height and the normal force had an angle of 0 between the two, and divided by time, which was 60 seconds or 1 minute. Plugging all those numbers into our calculator, we end up getting that the power of the escalator motor is 2,123.3 watts. All right, so that last one is probably the hardest one on the worksheet and the hardest example that we did today. So I hope that made sense. Now this last example 5, you will also see you have something similar to it in your lab this week that you guys are gonna be doing. So that should be fun. So I hope that you guys learned something today. Let me know if you have questions. You feel free to email me. Also, I did change office hours to Fridays from noon to 1 p.m. Okay, so I'm hoping that a later day in the week and also a little bit later time will not only give you more days to work on your homework, but more time to sleep in. So therefore, if you have questions, you can come to office hours. All right, I hope all is well, and I miss you guys, and I will talk to you soon.